be going out with the next paper presentation. The next paper ID is CMOS 2404. And the paper is entitled as Finite Element Model Updating based on RBF model and SO algorithm. Again, I repeat, paper ID CMOS 2404. Who is going to present?
I'm here. Can you hear me? Hi, can you hear me?
Yes.
Okay, I'll share. I can't share my PowerPoint.
Wait.
Okay. Can you see my PowerPoint?
Yes, it's coming out. It's still now not visible. It's sharing. Yes. Now your screen is visible.
Okay.
You make it full
hello.
screen? Yes, now
Okay,
it's
okay.
full screen. You can start.
Okay. Hello, everyone. Good afternoon. My presentation title is Finite Element Model Updating based on RBF model and SO algorithm. As aerospace technology developed, the use of computation simulation analysis instead of experimental verification has become an important means to accelerate the design iteration and save the research funds. The finite element model is the main method for the numerical analysis of aircraft structural dynamics. Due to the existence of errors in the model, the simulation model often fails to reflect the real model situation accurately, and the research on the model updating technology has received extensive attention. Currently, the mainstream parametric updating methods based on sensitive need to repeatedly call the finite element model for iterative solution consume a lot of computation resources. To solve this problem, it becomes a feasible approach to use surrogate models. This paper presents a method for model updating, which using radial basis functions and snake optimization algorithms. The radial basis function is used to establish a surrogate model to avoid resolving the simulation model for each iteration in the model updating. And the model updating problem is transformed into an optimization problem. And then the snake optimization algorithm is used to optimize the surrogate model. And finally, the guttural aircraft model is used to test the updating results. And the three-level confirmation criteria is introduced to verify the reliability of the update model, which in turn verifies the validity of the algorithm. The difference between the computed and experimental values of the model is used as objective function. As a result, the model updating problem is transformed into an optimization problem with the objective functions as shown in the PowerPoint. In the simulation process of several engineering cases, the radial basis function surrogate model has achieved good computation results. The analytical expression of the radial basis function as shown. Gaussian radial basis function surrogate model are the most commonly used form, and the main criteria of surrogate models as follows. Snake optimization algorithm is based on the simulation of snake behavior, which simulates the behavior of snakes in nature, including foraging, fighting, mating, and laying eggs. The algorithm can efficiently solve the optimal solution of the objective function. The initial finite element model is established and parameterized to facilitate model updating. The sample space is generated by selecting a suitable experimental design method based on the screened design variables. The radial basis surrogate model is established and the fitting accuracy is examined. The objective function is constructed, and using SO optimization method, the surrogate model is optimized by searching for food, fighting, and mating to search for the optimal solution. The optimization results are substituted into the initial finite element model for verification. The Gartner aircraft model is a standard aircraft model designed and manufactured to compare and evaluate different variable test analysis techniques. In this paper, the finite element model of Gartner aircraft is established by pattern. According to the structural characteristics of the physical model, the wing and the vertical tail are both the main deformation components in all orders of models, and the structural parameters themselves have significant uncertainties. Therefore, select 6 structural parameters as the input parameters to be updated. The details are shown in table. Simulation calculations are carried out for the initial model, and the experimental values are available according to the literature. The maximum error of the model frequency difference of the first 10 orders is 14.02%, and the average error is 5.47%, and there is a large error between the calculated data and the experimental data. Therefore, the dynamics model needs to be updated. According to the uncertain characteristics of the parameters in the finite element model processes, the input parameter variation range is set as shown in table. Within this design space, 8 levels are taken for each input parameter, and 6-factor 8-level experimental design is carried out, and a total of 64 finite element analyses are arranged, and the obtained sample data are used to construct a radial basis function surrogate model. The accuracy checking results of the surrogate model are shown in the picture. The RMSE and R2 tend to 0 and 1, indicating that the surrogate model has sufficient accuracy to carry out the subsequent model updating work instead of the finite element model. After establishing the surrogate model and verifying its accuracy, it is used as a surrogate model for optimization, and the SO algorithm is used to search for the optimal solution, where the initial population size is set to be 50, and the maximum number of iterations is 1000. The optimization objective is set to be first 10 orders of model frequencies. In the first 10 orders of the updated frequency, the maximum error is 3.31%. The minimal error is 0.06%, and the average absolute error is 1.43%, which meets the accuracy requirements of the project. The 11th to 14th order intrinsic frequency after the structure were used as evolution data for the model updating. The prediction results of the 11th to 14th order intrinsic frequencies are given in table. In the initial frequency values, the maximum error is negative 4.68%. The minimal error is negative 2.11%, and the average absolute error is 2.99%. The maximum, minimum, and average absolute error of the updated frequency values are negative 3.62%, negative 0.86%, and 1.88%, which indicates that the updated finite element model achieves acceptable prediction accuracy for the 11th to 14th order intrinsic frequency. In order to examine the generalizable of updated model, the predictable of the model after local modification of the structure is examined in this paper. The lambda mass located at the wing length is modified to 0.72 kilogram, and the results are shown in table. Relative to the initial finite element model, the average error in the prediction frequency of the updated model was reduced from 8.75% to 2.55%. The maximum error in the prediction results was reduced from 40.03% to 14.94% for the initial model, and the minimal error was reduced from 0.80% to 0.02%, indicating the third level predictive validity of the update model. Now is the conclusion. For the Gartner aircraft model dynamics updating problem in this paper, the surrogate model constructed by radial basis function only needs to be analyzed by finite element model in early stage, and the subsequent model updating process completely utilize the surrogate model, avoiding multiple iterations of the finite element model in the updating process, and improving the analysis efficiency. The SO algorithm was used to optimize the surrogate model, and the results shows that the updated model satisfies the three levels of prediction. The model has good reproduction and prediction ability of the updated frequency bands and the predicted frequency bands, and it can also predict the frequency after local modification of the structure. The updated model has some general applicability, which verifies the effectiveness of the model updating method based on RBF surrogate model and the SO algorithm. Thank you for listening.